Am I audible to all? Voice is fine. I think it is okay for everyone. Whenever any problem comes, please let me know. Okay, so shall we start now? Before starting the class, I would like to ask whether you have solved any test series, any previous year gate questions in the last few days, and you faced any problem or any doubts you have. Please immediately let me know. Any doubts till now, whatever I taught in the classes. So any doubts with any concept which is not clear to you, can immediately ask. So in starting, I can resolve all the problems and then I'll start from fresh. Okay. Any doubts? Anyone who is facing any doubts, any problem, you have immediately ask. I think all concepts are clear. So we can start from fresh. I was talking about transistor. I already talked about diodes. So diodes are over p-n junction diodes, their capacitance and their depletion width and all everything, it was clear. So it was done. Any doubts if you have in that also you can ask. And now we'll come to the transistor. The basic difference between these two devices is there is a controlling capability in the transistor. We can control the flow of the current through the transistor. But in diode, we cannot control. Once it is on, we can flow any amount of current. So those things, those are the differences. And one more thing, that it has three terminals and diode was having only two terminals. So a lot of differences you will see in the coming concepts. So the transistor is totally different from BJTs and diodes. So in transistors, I clearly explained the various type of transistors. So among them, the basic transistor was BJT, bipolar junction transistor. Why it is called bipolar junction transistor, that also we'll discuss. So in the last class, I talked about the modes of operation of a transistor. So in this, we have four modes. One was cutoff mode, second is saturation, third is active, and fourth is inverse active. It was these modes are totally dependent on junction biasing, emitter junction biasing and collector junction biasing. So based on those biasings, we decided that these are the modes in a transistor. So all these I discussed in the previous class. So today I'm leaving this, and now I'll start with the active mode, the flow of current in active mode. So for active mode, we have emitter junction is forward biased and collector junction is reverse biased. Here it is not emitter, it is collector. C. So collector junction is reverse biased. And I am talking about a transistor which is PNP transistor. P is the emitter, N is the base, and P again is the collector. So PNP transistor in active mode I'll discuss, and this will be the basic transistor for me for the coming classes. So here the emitter will be at a higher potential and collector will be at lower potential, that I told you earlier, and the base at the medium potential. As shown in the figure, we can see the emitter terminal, which is at this point, it is at highest potential and its negative was connected to the positive of this. So means this is the lowest one. We can say here if it is 0 volt, so we will say this is not 0 volt, it will be having some voltage like 2 volt, 5 volt. And if it is 5 volt, then with respect to this terminal 5 volt, this voltage will be maybe 12 volt. So this cell, this is voltage source, it will be of 7 volt here in this case if we consider like this. So we can see it is at 12 volt, which is at highest potential, 5 volt, that is the base, which is at medium potential, and the collector is at lowest potential, as I mentioned in the lines. So we can see in this way. Now we will discuss the basic things inside the transistor, how transistor is working, how transistor is controlled by the external current source and all. So with those things, we'll discuss all the basic concept about the transistor, how what is happening inside and what are the different parameters used in transistor case. So that we'll see. So here my main aim is to make you understand all the basic things related to transistor, so that there should not be any confusion. One time one question I found, which was in UPPCL, Uttar Pradesh Power Corporation Limited. In that I found one question that was based on emitter efficiency they asked. So that question I'll take later, but the concept behind that I'll discuss here. So here what is this emitter efficiency? I think basic things I discussed already. What are the basic things in this? We had three currents, that is IE, IB and IC. In the previous slide we can see we have three currents. One is IE, second is IB and third is IC. So here I'll consider all currents coming into the device. Remember, so here this is IC, this is IB, and this is IE, this is IB. So all three currents, these are coming into the device. Okay, so that I'm considering here. So based on their sign, whether it is positive or negative, its direction will be decided later. But at a starting, I will consider all the currents are entering into the device. So that is my concept here. So this because of forward biased of emitter junction, we can see I told you the emitter junction is forward biased and collector junction is reverse biased. Because of this forward biasing, the majority charge carriers, which are holes in emitter, are passing through the junction, or these are diffused into the N region, that is base region. Because it is forward biased, so diffusion takes place. So these majority charge carriers, which is hole, it will diffuse into the N type semiconductor, that is base. So like based on this, these majority charge carriers will be coming in base region and they are crossing the base region and reaching the collector region. How it is, that we'll see. So here I can show you IPE is the current due to the hole coming from emitter to base to collector. So that is IPE. So total charge carriers which are diffused into the base region. That is the current, that is whole current, and it is crossing the junction, emitter junction. And second thing, INE, that I'll tell you. So I can show you the base produce current IPE and electron flow from base to emitter producing current INE. See, electrons which are diffused into the P region because it is forward biased. In forward biased, majority charge carriers will be crossing the junction. So majority charge carriers in the emitter region, that is P-type region, holes will be there. These will be crossing the junction, and the majority charge carriers in the N region, these will be crossing the junction and reaching to the emitter terminal. So like that, these charge carriers will be crossing the junction. The whole current will be IPE and the electron current will be INE. So remember, electrons are coming from base to emitter, but current will be opposite to the flow of electron. So that will be towards right side, this direction, that is INE. So these two currents are crossing this emitter junction. That is clear here. So the net current through this emitter junction will be what? The sum of these two currents. Sum of these two currents. Okay, I have not mentioned here. I'll write here sum of these two current, that will be IE is equal to IPE plus INE. Okay, these are the two currents here. So the IE is the total current which is entering here. So this current will be the sum of these two currents, IPE and INE. These are flowing in right direction. So that is equal to IE. So here we can see emitter is much heavily doped in comparison to base. Okay, it is much heavily doped in comparison to base. Base is lightly doped. So the current IPE is very greater than INE. Means I can write IPE which will be very greater than or very greater than INE. It means I can write IE is approximately equal to IPE because emitter is heavily doped. Very few electrons will be entering into the P region, means into the emitter side. So that is why INE is very less as compared to this. So the current which is dominating here and which is crossing the junction will be only the whole current, okay, which are coming from emitter. So now we'll come to the concept of emitter efficiency. So what is this? It is, in the next slide I have written, it is the ratio of current through emitter junction due to carriers of emitter and the total current through emitter junction. It is represented by gamma. It means gamma is equal to the current through the emitter junction due to the carriers of emitter. It means carriers of emitter are holes. So IPE it is talking about to the total current through emitter junction, that is IE. IPE divided by IE. So this is for P and P. You can say, and gamma is approximately equal to 1, or it is, we can say, less than 1 always. It is slightly less than 1, slightly, approximately equal to 1 or slightly less than 1, we can say, because IPE is approximately equal to IE. In the previous slide I have written, IE is approximately equal to IPE. So we can say gamma is approximately equal to 1, but it is not exactly 1, it is slightly less than 1. So this is for PNP transistor. If I will talk about NPN transistor, I will write gamma will be equal to INE divided by IE. That is for NPN transistor. So for this also, gamma it is slightly less than 1. Okay. So now what happens? This is, I think, clear. What is emitter efficiency? Emitter efficiency means total current due to the majority carriers in emitter to the total current crossing the junction. That is the ratio they are talking about. So now, when holes enter the base region, when these holes enters the base region, a few of them recombine with the electrons present in the base region, and remaining holes reaches the collector junction in the form of IPC. That is, I have already given here. Holes are coming from emitter region, they are entering into the base region. Few holes, or out of 100 we can say 1 or 2 holes are recombined with the electrons present in the base region. Remaining holes will be crossing the base, this collector junction, and reaching the collector. So how these carriers are reaching the collector junction? See, reaching the collector terminal. So how? Here we can see it is a collector junction. Here wrongly it is written, it is not a base JB, it is JC. This JC, it is reverse biased. These holes which are in base region, these holes in the base region are minority carriers because it is an n-type material. In n-type material, we have minority carriers. Those are holes here. So these holes in the n region, which are minority carriers, they will experience some attraction towards the junction because it is reverse biased. So in the reverse bias junction, minority carriers can cross the junction. So these holes are minority carriers in the n region, and they can easily cross the junction. They don't experience any repulsion at the junction because it is reverse biased. If it is reverse biased, then these minority carriers can easily cross the junction. They can reach the collector junction. That is why in uh, active mode we use, it is forward biased emitter junction and collector junction is reverse biased. So, and this is also called amplifier mode, amplification mode, active mode. So that we will see later what is the amplification mode, but I'm talking about active mode here. So these minority carriers, which are holes in n region, in the base region, can easily cross this collector junction because collector junction is reverse biased, I made already. So that is the main thing here to remember. Now, when these holes, they will reach in the collector. So the current in the collector region due to these holes is represented by IPC. IPC. IPC is the, we can say, IPC that I have mentioned here. It is the hole current through collector junction through JC. Okay, so that is we need to remember. Here I already mentioned IPC is the current passing through the collector junction. Now we will come to the next concept, which is With these holes reaching the collector region, new term comes. What is the term? Transport factor. Means transportation of majority carriers from emitter region to the collector region. That is the transport factor. Now, what is the definition? It is the measure of efficient transport of carriers from emitter junction to the collector junction. So, it is represented by, mathematically we can say, it is represented by alpha t. Transport means alpha t, or it is also represented by beta star. So this beta star is the transport factor, and it is equal to IPC divided by what? IP means total charge carriers which were started from emitter region and total charge carriers which were reached to the collector region. So that is the main concept here. So their current ratio is called transport factor. We can see IPC is always lesser than IPE because IPE is the maximum value, IPC is greater value. So smaller value, because few electrons, few holes are recombined in the base region. So out of 100, only 2 are recombined in the base region and 98 are reached in the collector region. So 98 divided by 100, that will be my transport factor. So that is here represented by IPC divided by IPE. So the whole current in the collector region to the whole current in the emitter region, that is the ratio, which is called as transport factor. We can see its value is also less than 1, always remember. But it is not that much, it is also slightly less. There is a less difference between these two, and there was a less difference between IPE and IE also. So this is, we need to remember. So here I have written some concept behind this, what is happening inside the device. That is, I have written words, so you just understand those. By keeping the base region narrow in width, recombination can be reduced. That is the main concept. Base region we keep very less, so recombination is very less. It means it is negligible. Second thing, the reverse voltage causes the holes to travel from N-type base to P-type collector. Why? That I already discussed. From N-type base to P-type collector, how they are crossing this reverse voltage, reverse bias junction. Because holes are minority carriers in N region, and minority carriers can cross the reverse bias junction always. So it helps the holes in crossing the junction. Therefore, the current IPC flows through collector region easily. That is main thing we need to remember here. Second thing, due to the recombinations in the base region I'm talking about. So due to the base recombinations, equal number of holes and electrons are lost in the base region. If base region keep losing electrons in the recombination, then it may become positively charged. Holes which are coming from emitter region, they are lost in the base region. It means they have taken some electrons from the base region. If they have taken some electrons from the base region, then it will be a electron deficiency in the base region, and electron deficiency is called positive charge. That is why it is positively charged. Which region? It is base region, which is positively charged. It opposes the movement of holes. Now when it becomes positively charged, that is base region, it opposes the flow of holes which are coming from emitter and going towards the collector. So it opposes the movement of holes from emitter to collector. Therefore, compensating the electrons should be provided to the base region, whatever electron are lost in the recombination, the same number of electrons should be provided by the negative terminal of the battery. So from the external biasing supply, that is, so that base region remains neutral. If base region remains neutral, means the holes coming from the emitter region, they won't experience any repulsion and they will be freely moving through the base region. That is the main aim, to supply electrons to the base region. I think it is clear. Any doubts if you have, please ask. Okay, so now I'll move on. So that was the concept behind this. So now what is the current in the base region? The compensating electrons flowing into the base region constitute the base current. This current is equal to what? IPE minus IPC, because the IPE number of electron holes are started from the emitter region. Some holes are lost in the base region and IPC electron holes reached in the collector region. So total started minus total received, that will be the base current, that is a small region current. So this base current here I represented, that is this base current. What is this? IB. I can write IB is equal to IPE minus IPC, and this is the recombination current. Recombination current. Remember, this is the recombination current, and it flows only when recombination occurs inside the base. Now, if there is no recombination, means there is no base current, and that cannot be possible. A little or few recombinations will be there. So because of these few recombinations, there will be a base current. So it flows only when recombination occurs in the base region. That is, we need to remember. Second thing, now if electron supply to the base region is increased, base becomes negatively charged and attracts greater number of holes from the emitter. As a result, holes flow from the emitter to collector increases. Obviously, large number of holes will be attracted towards the base region and they will be crossing the base region and going into the collector region. So this increases. If an electron supply to the base is reduced, this is if electron supply to the base region is reduced, base becomes positive, right? And it attracts less number of it attracts less number of holes from the emitter. Due to this, the hole flow from emitter to collector decreases. Thus the electron supplied to base, it is electron supply to base or base current controls the carrier flow from emitter to collector. That is the main concept here. See, if we increase the electron supply, it will attract more number of holes and base current increases. If we supply less electrons or we supply less electrons, then it will be positively charged, so more repulsion takes place. So base electron that emitter current decreases. Emitter to collector charge carriers flow decreases. That is why this current decreases. So base current only can control the flow of charge carriers from emitter to collector. That is the main concept here. And because of that only, the BJT is called as current control device. That is here. Current controlled device means output current is controlled by the input current. That is base current. So by base current we can control the flow of the current from emitter to collector. So that is why it is called current controlled device, BJT. Remember, and we will talk about what type of devices FET and CMOS are there. That also we'll discuss, but here it is the current controlled device. So now is there here? Okay. Here we can see few things. That is the reverse voltage, which is collector to base voltage. We can see here. I will make one device. This is PEV. This is VCV. This is P, N, and P. This is emitter, collector, and base. So here we can see reverse voltage, that PCV, this one. Because of this reverse voltage, an additional current I naught also flows through the collector junction. See, this is reverse biased. And this reverse biased, I talked about the current, that is IPE. But I have not talked about the current ICO. ICO is what? That reverse current ICO. That is reverse saturation current through this junction. I discussed that IC will be this. Okay, so here now I talked about IPE. I have not talked about ICO. ICO is the reverse saturation current through this reverse biased junction. So conventionally I can say it is indicated from collector to base. This ICO, it will be flowing opposite to the reverse YC. So here ICO will be negative. ICO, its flow, it is from collector to base. That is why it is negative. That is why I'll consider it in this direction. Second thing, ICO, it is in which region? It is in PNP. I'm talking about PNP. If I will talk about NPN, it will be positive in NPN. Remember. So if I apply KCL at this terminal, this point, so I'll see through KCL IC plus IP. This is not E, this is IPC. Remember, IPC. These two current are entering to the junction minus ICO. This is moving away from the junction, that is equal to 0. KCL at C. So that is IC plus IPC minus ICO equal to 0. From here I can write IC is equal to ICO minus IPC. That is here, that is the collector current. IPC, I know, I told you, it is the majority carrier current, and ICO is the minority carrier current. So from this expression, I can clearly tell you the collector current is the sum of two type of currents. That is majority carrier current, and second is minority carrier current. So the collector current is it is sum or difference, that is different thing, but it is depending on two charge carriers. that is majority and minority carriers. Because of that majority and minority, this BJT device is called as bipolar device. That is why it is called as BJT. The direction of IPC and IC are opposite. Yes, these are opposite. That is why I applied KCL. Remember KCL, what does it say? It says the current entering the junction, the sum of current entering the junction is equal to 0. That is KCL. KCL means the current, the algebraic sum of the currents entering to the junction is equal to 0. That is I have written here. And the current which is moving away from the junction, that will be taken as negative. That is why sum is 0. So from this I can clear. Okay, that is good. Okay, so now BJT, it is called as bipolar device because the collector current, which is our desired current, the desired current, it is depending on the two type of current, that is majority current and minority current. That is why it is called as bipolar device. So I think we understood the concept of bipolar, why it is called as bipolar, why it is called as current control device, that also I discussed in the previous slides. So as collector current is the combination of both majority and minority carriers current, this device is called as bipolar device. That is clear now. So now next thing, what is next thing? Next thing is the whole current through emitter is the drift current. Why it is drift current? Because in the emitter the holes are moving due to the external supplied voltage. So because of that external supplied voltage, the current in the emitter region is the drift current. Next, the whole current through the base region is diffusion region. Why? Because majority carriers are diffused into the base region and some majority carriers are recombined, and that recombination current is the base current, and it is due to the diffusion of majority carriers from the emitter region. That is why it is called as diffused current or diffusion current. The base current is the diffusion current, and the whole current through the collector is also drift current. That is we understood already, because that in collector carriers will be moving because of the external supplied voltage. So we can see how it is diffusion, how it is drift. So whole current through the collector region is due to drift. So that is why it is called as drift current. So we can see here the BJT current flow is due to both drift and diffusion mechanism. So it has both type of current, drift current and diffusion current, that we have to remember. That is some few points. These are few points we need to remember. So based on that only we can understand the working of any transistor. So I think this is also clear that drift collector current is a drift current, and the mechanism due to which BJT current flows, that is drift current and diffusion mechanism and diffusion mechanism. So these two mechanisms we have here. Now I think it is clear everything for you till here. Next we will see what is called as large signal current gain. What is this large signal current gain? It's a definition I have written. The ratio of negative of change in collector current to the change in emitter current. Change in collector current to the change in emitter current. Why? And it is why it's negative, that you will see clearly. Why it is negative and why? That is large signal current gain. Current gain means current divided by current. So change in collector current to the change in emitter current, and the negative of that is called as the large signal current gain. And it is represented by what? Alpha. So this is not alpha t, it is alpha. And alpha is equal to delta IC divided by delta IE. So that is, here we need to remember that delta IE is large. Remember. So large signal current gain it is because delta IE is large. So here we can see the large signal current gain, that is the ratio of change in collector current, emitter current with the negative sign. Sorry. So here I think it is done, that alpha equal to minus delta IC divided by delta IE, where delta IE is a large value. Now here if we see what two types of currents, IE and IC, what happens? If IE is 0, suppose I will write here like this. If IE is 0 value, then IC will be equal to IC not only, ICO. That will be ICO, because if IE is 0 means IP is 0. IP is 0, then IC equal to ICO only. And if IE is not equal to 0, means some majority carriers are generated in the emitter region and moving towards base. So IC will be equal to IPE, sorry, ICO minus IPE. That expression I already given. This will be the collector current here. So if it is 0, it will be reverse saturation current only. If it is non-zero, it will be the reverse saturation current minus the current due to the majority carriers coming from the emitter region. So here the change of IE from 0 to non-zero value is called as large signal change. That is delta E, that is non-zero value, zeros and non, from 0 to non-zero value. If we have this, then this is called as large signal change. Sorry. So large signal change. So here I can write next. I've written something here. I think the change of IE from non-zero to non-zero value is called as large signal change. Here I can write delta IC is equal to ICO minus IPC, that I already given, minus ICO, that is equal to minus IPC. That is change only I want to show you. I want to show you the change, because IPE is equal to ICO minus IPC, and that is minus ICO. This is equal to IPC. And delta IE is equal to IE minus 0, that is equal to IE only. So I can write alpha now, IPC divided by this IPC divided by I, and it is plus sign, and it is plus sign. So alpha equal to IPC divided by IP. So I can write IPC divided by IP into IP divided by IE. So this value is called as beta star and this value is called as gamma. So alpha equal to beta star into gamma. Remember, this is the only thing here. Alpha equal to beta star into gamma. That I got alpha equal to beta star into gamma. So this expression we need to remember, that large signal current gain is equal to transport factor into emitter efficiency. Transport factor into emitter efficiency. That is only the expression we need to remember. I think it is clear. For all, both beta star and gamma both are less than 1, so alpha will be less than 1. Remember, so large signal current gain alpha. Now we'll talk about something, base current. So what is base current? For base current, we will apply KCL at base. See, diagram will be same always. Whatever diagram I have given, that will be same. So at the base only I will apply KCL. KCL at base. Okay. So in this case, IB, which is entering into the junction, plus IPE, which is coming from emitter side into the junction, minus IPC, it is going away from the junction, plus ICO, which is coming towards the junction, towards the base region, plus INE. These all are the currents which are entering into the base terminal from all sides. Okay, so I think I can write IB is equal to minus IPE. What is this? This will be going this side, plus I can write IPC, then minus ICO, then minus INE. So these are the things. So here, suppose I will take minus sign outside, I'll get IPE minus IPC plus ICO plus INE. Suppose minus sign I have taken out. So here we can see this factor. This is different and this is different. We can see ICO is the reverse saturation current and it will be in nanoampere for silicon and picoampere, in microampere in germanium, which is very less. Second thing, it is INE. Very few electrons are entering into the emitter junction, emitter region through the emitter junction. So that is INE. It is very small. So these two both are very small, and this is dominating. This is dominating factor and this is ignoring factor. We can say this is ignored and this is dominating. So from this I can write IP is equal to, or approximately equal to, minus IPE minus IPC. That is the recombination current. See, all these derivations will not be coming in your exam, but the concept behind this can be possible. So here I got the base current which is equal to minus of IPE this. Sorry. So I think this concept is clear. There's no doubt in this concept related things. You have still, you can freely ask in the chat box or in your voice. You can discuss, you can ask questions. So here, this I got, that is base current. So after base current, we'll come to the collector current. So collector current, we already seen how it was depending on minority and majority carriers. So when our BJT, if it is in the active mode, so our IPC, sorry, IC is equal to ICO minus IPC. That is, I already talked, I already explained. And now this IC, we can write IC is equal to ICO, minus sign is there, IPC will be equal to alpha into IE. Alpha into IE. So ICO is equal to ICO minus alpha I. So here we can see it is like one expression. Sorry, it is, I will write one expression. So we have seen all currents which are IB, IC and IE, they were flowing into the transistor. So their sum was equal to 0. Means I can write by KCL IP plus IC plus IE. All three will be equal to 0. Their sum will be equal to 0. So from this I can write what is called IE. This is alpha. Sorry, this will not be like this. IE, I can find out minus IB plus IC. So here equation 1, I can write it, this is equation 2. So here IC is okay. Now IC is equal to alpha into IB plus IC plus ICO. Okay, I think it is clear. IC is equal to alpha into IB plus IC CO, because I is equal to minus alpha minus IB plus IC. So I just replaced this IE value in this expression, in this first expression. So I got alpha IB plus IC plus ICU. That is only. So now this IC, it will come here. I'll write IC into 1 minus alpha is equal to alpha IB plus ICO. It means what I'll write, IC is equal to alpha divided by 1 minus alpha into IB plus ICO divided by 1. So here we are getting, see, two different values, alpha divided by 1 minus alpha to IB plus ICO divided by 1 minus alpha. So we know alpha by 1 minus alpha equal to beta, and 1 plus beta is equal to 1 by 1 minus alpha. I can calculate from this. So here I can write beta IB plus, this is 1 plus beta ICO. That is, I can write third equation. So I think IB IC is equal to beta IB plus 1 plus beta CO. This is the general expression for any collector current. We need to remember this. This is the correct one. We need to remember IC is equal to beta IB plus 1 plus beta ICO. Very simple, all the things we can directly remember, we can directly use, or we have some other parameters we can understand easily. So here what is beta? Beta is called large signal current gain of common emitter configuration. Here beta is the large signal current gain. Sorry. Beta is the large signal current gain of a common emitter configuration. Any common emitter configuration, its large signal current gain is called as beta. And alpha is the large signal current gain of common base configuration. So alpha and beta both are clear, I think. For common base configuration, it is the large signal current gain that is called alpha. So beta is equal to, in the next slide I can write collector current I was talking. Beta is equal to alpha divided by 1 minus alpha. One thing. Then now next thing I can write alpha is equal to beta divided by 1 plus beta. And 1 plus beta is equal to 1 by 1 minus alpha. These three things I need to remember. Alpha divided by 1 minus alpha. Alpha equal to beta divided by 1 plus beta. And 1 plus beta is equal to 1 by 1 minus alpha. We need to remember. So now if we take equation 3 here, I'll get IC. Equation 3, if I take IC minus ICO is equal to beta ICB minus plus IC. So I think it is clear that beta ICB IB plus ICO, and ICO is taken this. So now I can write what is called beta, that is equal to IC minus ICO divided by IB minus ICO. So here I can write delta IC divided by delta. With this is our beta. Beta is delta IC divided by delta IB. So these are the basic things we should know about the transistor. Then only we will be comfortable with the things provided, and the questions also will be comfortable. So here we can see what is beta, delta IC divided by delta IB. That is that ratio it is. So we should know all these formulas. We should remember. Now we'll come to another concept that will be coming here. That is DC beta of a transistor. DC beta of a transistor. It is the ratio of DC collector current to the DC base current. That is DC collector current to the DC base current. Or I can write beta DC is equal to IC divided by IB. Collector current to the base current in DC case. That is. And ICU is very small in DC case because saturation current is very small. So beta DC is equal to beta. So I can say here that beta DC is equal to beta. Why? Because ICO is very small. So that we can drop. If we drop, we will get beta DC is equal to IC divided by IB. That is the one thing. Second thing, the AC beta of a transistor is the ratio. Sorry, it is not a ratio, it is the rate of change of collector current with respect to the base current. Means beta AC is equal to change in collector current, sorry, delta IC divided by delta IB. That is equal to delta IC divided by delta IB. Directly we can understand this. Delta IC divided by delta IB when delta IB is small. Delta IB is very small. It is very negligible value or very small value. Delta IC upon delta IB. Take. So from the above equation which I mentioned, that was three equation. From that three equation, I can write IC is equal to beta IB plus 1 plus beta ICO. This is IC is equal to beta IB plus 1 plus beta IC. We can differentiate this. So if we differentiate, we'll get DIC divided by del IB is equal to, it's called beta AC and this is called beta plus d beta divided by d IB. To differentiate the above equation, we'll get beta AC, that is this beta into dIB upon dIB, that is 1, and again d beta divided by dIB into IB with respect to IB only we are doing. So here, so I can write d beta upon dIB into IB plus we can differentiate this 0 plus 1 into, oh sorry, it's a little mistake I'm doing. 0 plus beta divided by dIB into ICO means beta plus d beta IB into this d beta upon dIB. I can take out common. So here we can see beta plus d beta upon dIB into IB plus ICO. Here, what we do, we'll consider beta is independent of IB. If beta is independent of IB, in that case, if beta is not depending on IB, it is not depending on IB, in that case d beta divided by dIB is equal to 0. In this case, that beta AC, which is given as this DIC, divided by dIB, and that is equal to d beta divided by dIB equal to beta. That is beta AC is equal to d beta upon dIB is equal to beta. We can directly write beta AC is equal to beta if beta is not depending on IB. In the other case, beta AC DC was also beta. So these two were clear. So from this, I can tell you now what are the next thing here. The conclusion. What is the conclusion here? Conclusion is first, beta DC equal to beta AC and equal to beta in numerical questions. We generally take this because there is a little difference, that is a minute difference that can not make big differences. Okay. Second thing, beta is a measure of the amplification. Second thing, beta is a measure of amplification ability of the transistor. Means transistor is having ability to amplify any signal. A transistor with higher beta can act as an excellent amplifier. Higher beta is missed. Higher beta can act as excellent amplifier. Okay, so that is the second thing we need to remember. Third thing, if alpha is tending to 1, then beta will be tending to infinite, because beta was written as alpha divided by 1 minus alpha. If it is reaching towards 1, this term will be 0. So this will be some value divided by 0 will be infinite. So it is clear. Now next is to have a transistor with large alpha. With large beta. Here beta is not written. Alpha should be as closer to 1 as possible. We want to have large transistor beta, so alpha should be closer to 1 as possible. Very minute difference can be possible, otherwise it should be equal to 1. That is here we can consider. Okay, so that is our beta and alpha equal to 1, then beta is equal to finite. So that is that point. Any doubt? Any doubts? Anything? Am I audible, clear, or anything which is not clear here? Please let me know if you have any confusion or anything you are not able to listen. Okay, clear, I think. So here that was the point. Second point. So third point, it was like to have a transistor with large beta, alpha should be as close as possible. To make alpha closer to possible, see, to make alpha closer to what? 1. What I am to do? First thing is Ne concentration will be, sorry, it is wrong. Ne will be very greater than Np. Remember, emitter doping should be far greater than the base doping, so that emitter efficiency gamma is equal to 1. So that emitter efficiency, which is gamma, that is equal to, or it is coming to 1, near to 1. Emitter efficiency, that is only alpha should be very close to 1 and beta should be very large. So for that, emitter efficiency should be 100%. Second thing, the base width much will be much smaller. Base width will be much smaller than diffusion length, due to which transport factor approaches to 1, so that beta star should be approaching to 1. So that is the main thing here which I have taken, that WB, if it is very less than LP, so in that case beta star will be 1, means this is transport factor. It was emitter efficiency, this is transport factor is nearly equal to 1, means whatever electrons started in the emitter region are easily reached to the collector region. There is no recombination, almost very negligible recombination, means out of 100 we have 1 only, or out of 1000 we have 1 or 2 recombinations. So that factor matters, and that is here taken. Okay, I think it is clear for all. This doubt is also clear for all. Anything which is not clear, let me know immediately, please. Okay, I think it is clear. Any doubts, anything which is not clear to you? I can again explain. I can give you a clear idea then after. Okay, so I think it is clear. So here now I'll come to the another concept, that is ICBO and ICEO. So for this you just wait for 2 minutes. I'll come back. We'll take 2-3 minutes break. Okay. Okay, let me start with this. So what I was talking about ICBO and ICEO. So what is ICBO? ICBO, as name suggests, it is the collector to base current when emitter terminal is opened. It is collector to base when emitter terminal is opened. Means we have circuit like this. We have collector, emitter and base. When this terminal is open, this terminal is open, you can see. So this is collector to base. So that is IC collector to base current when emitter terminal is open. This is emitter terminal is open circuited. So this is equal to IC current when IE is 0. IC current when IE is 0 and IC current when IE is 0 will be equal to ICO. That I already told you long back. When emitter terminal is open means ICE is 0. If there is no ICE, it means there is no majority carriers which are reaching to the collector junction. So IP is 0. If IP is 0, IE is 0, then IPC will be 0. IPC will be 0, then only reverse saturation current will be existing. That is ICO. So that is collector to base current when emitter terminal is open. You can note down that also. Second thing, ICEO. ICEO is the collector to emitter, or it is the collector current when base terminal is open. So that is ICEO. ICEO, this the circuit diagram will be like this. Your system is working, and what you did, it was here and here. What you did, you made open circuited. When base terminal is open, emitter is connected. E, P and C. So in this case, this ICEO is the current which is equal to IC when IB is 0. When IB is 0, in this case, what will be the work current expression? 1 plus beta IC. It means ICO divided by 1 minus alpha. You remember this, how it came? IC is equal to beta IB plus 1 plus beta ICO. So you can see if this term, this IB is itself 0, then what is the value IC plus beta ICO? The ICO divided by 1 minus alpha. You can write in this way. So I think it is clear. So here we have done this. Now we have question based on the previous concept, whatever I have taken. So based on that concept, I have the value of transistor as beta is equal to 49. Emitter injection efficiency they have given, that is 0.995. What is the thing they wanted to ask? Base transport factor. Can you give me answer for this question? Can you give me answer for this question? I want answer for this question, please, immediately. Please all of you solve the question. I want answer quickly. Very simple it is. You know all the values, all the formulas, you know. Okay, 0.98. Yes, correct. Its value is 0.984. Remember, if it is in pointer, it will be they will be asking up to 3 decimal points. They will be asking the question answer for 3 decimal point. I think all of you are cleared with this concept. How they got this answer. Anything else you want, I can write. I can give you solution also if you want. So please tell me. All of you understood the concept, or shall I solve the question? Please don't leave it as it is. You have doubt, immediately ask. I'll give you answer. I'll give you solution also. What they have given, immediately please tell me what they have given. Beta is equal to 49. That is only what they want. They want beta star. That is transport factor they want. So alpha, we know alpha equal to beta star into gamma. So beta star are different. Beta star they want, right? So beta we have, so alpha we can calculate. What is alpha? Alpha will be beta divided by 1 plus beta, means 49 divided by t is 0.98. This now. One more thing they have given, emitter injection efficiency. Emitter injection efficiency gamma also they have given. How much? 0.995. So I can write beta star is equal to alpha divided by gamma. Alpha is 0.98 divided by 0. The value is 0.984. So any doubts if you have, please ask. Please let me know the doubts. I think it is clear. Okay, quickly ask the doubts if you have. Otherwise, I'll feel it is correct. It is clear. Now, I'll give you the one more point here. What if a collector is short circuited with, I have some symbol of diode which is made here like this, and here it is disconnected, and next sorry, this is not arrow is this here. So what is happening here? This minus VB plus. Okay, this is this circuit, plus minus and plus minus. So if a transistor collector is shorted to the base, what it behaves? If it is shorted to the base, it will behave as a diode. This type of diode it will behave as. Arrowhead indicate the direction of electron current in emitter. Arrowhead, it is the electron in emitter. Okay, so I think it is clear that if it is shorted with the base, collector region is shorted with the base, it will act as a diode. So it will be acting as a diode. So diode positive terminal we know and negative terminal we know here. So current through this transistor will be controlled by what? Voltage VBE. In this, whatever current will be flowing, that will be controlled by this VBE, which is applied across the emitter junction. So the current flow is like this. What the current flow it will be? Okay, the next which I will go here. So here JC, here JB, or this. And this output will be positive, this negative output. This is the current I. Okay, so it is like this. It is looking like this actually. This collector junction, this is base junction, this. So it is N type of transistor. So here electron, they will be moving from here and they are moving from here to here. Okay, N to P, negatively charged, is forward biased emitter junction. It is now diffused into the base region. So due to this forward voltage VBE, which I have already shown, electron will injected from emitter into the base region. These electrons then cross the collector junction due to the built-in potential present across the collector junction. We have collector junction, we have built-in potential across this. So these electrons get the junction. So the carrier flow takes place through collector junction even though the collector and base terminals are short together. Collector and base terminals, they are short together. But even we have base terminal are short circuit together. So understood? I think. Okay, this one you want to repeat me. Okay, what is this? This is water due to the forward voltage VBE, whatever voltage I applied across this terminal here, this is VBE. Due to this forward voltage, what will happen? Electron will be injected from emitter to the base region, and these electrons are minority carriers in base region, and they will be now crossing the junction to reverse biasing of JC. right? So these electrons then cross the collector junction due to the built-in potential present across the collector junction. Thus, the current flow takes place through the collector junction, even though the collector and the base terminals are shorted together. Okay, so that was the concept behind this. Collector and base terminal are shorted. After that, also the electrons are reaching to the collector junction. Now, current through a diode connected transistor can be calculated using diode equation. So diode connected transistor, if we have, so in that, what is the current which we can get? I say I is equal to I naught e to the power V divided by eta Vt. This is the actual expression. I is equal to I naught e to the power V eta Vt. Okay, so I think you understood. It will be acting as a diode now. So now, what is I naught here? I naught is the reverse saturation current of emitter junction. Whatever emitter, I naught is the reverse saturation current of emitter junction. That is, here in this case, I naught is equal to IE naught. And IE naught here, eta it is equal to 1 VF is a transistor. And V is equal to VBE. And here E equal to VBE. It is so. Now I can be converted as IEO e to the power VBE divided by T divided by ET. Cos eta we have taken 1. So now one question I have, you can please note down the question. I was not able to write the question here, so you just note down the question. In a figure shown that I'll show you, transistor has VBE. Transistor has VBE that is equal to 0.7 volt, and reverse saturation current of that is I naught is equal to 10 to the power minus 10 to the power minus 13. Okay. It is at room temperature at 300 Kelvin. What they want? Current I is current I. Circuit is what? Okay. This emitter terminal closed, plus minus E. Okay. So this is what we are talking about. So in this diagram, we need to calculate the current I. What is the I current here? Can you please answer the question? Please answer. Please answer quickly. Please answer quickly. .049 milliamps. Yes, correct. Answer is 49.26 milliamps. It means 0.049. That is amps. So I think it is clear. I have no need to write. Expression I have already given you. I note, that is IE note they have given. So all the values you know. You can just keep and get the answer done here. So it is so simple. Let me write I is equal to IEO here, e to the power PV divided by VT. That is the answer here. BB is given, VT we know, and IE0 also they have given. So now I'll come to one more question. You just note down. A transistor, that is the one of the good questions. A transistor, it has IB is equal to 25 microampere. It is microampere, and ICO will be equal to 100 nanoampere. And next thing what they have given, beta is equal to 100. Calculate IC, IE, ICVO, ICU. All you need to calculate. So I think you are perfect with the answers, perfect with the concepts. So if you good in your concepts, you can answer this question also. What are the values for one by one? You just try to solve, try to get the answer. Just try to get the answer quickly. Quickly answer this also. Waiting for your answers. Anyone who got the answer, please quickly all the values you have. many answers you got. It is not that much tough. Here, what is IC? The IB plus 1 plus beta. CO beta IB is 100 plus 101 into 100 into 10 to the power minus 9. These are the values we can keep and we can get 2.5 milliamps. This is the correct one for first. Now IE is equal to what? IB plus IC. And if it is minus 2. So I think I can keep the values 2.5 milliamps plus 25 microamps. So minus 2. This is the correct answer. So here we can see the negative sign I indicates that IE flows out of the transistor. IE is it is coming negative, it means IE flows out of the transistor, because we have all concept taken as I entering into the device, B entering into the device, C entering into the device. If it is coming negative, means it is out of the device. So that is why here negative sign says that I indicate that I flowing out of the transistor. Out of transistor it is flowing. So here I can write ICBO. Is this ICBO? That is equal to ICO. That is, they have given 10 nanoampere, 100 nanoampere. And next is ICEO. 1 plus beta to IC. And 0.01 is so. I think I will give you one question. Okay, so one more question you just note down that you try by yourself, so that it will be done quickly, because I don't have all the things. So you just try by yourself. In a circuit shown, PBE is given to us. I'll write somewhere else. Here I'll write. Question is what PBE they have given. That is 0.7 volt. Beta they have given is 100. Negligible reverse saturation current means ICO, it is nearly equal to 0, approximately no saturation current. So here also they wanted to know IC, IB and ICO. These are the things I need to remember. And the circuit is 5 volt, 200k is 3k, this is 10 volt, plus minus, plus minus, dB, and this is I. So these are the values, all values you have given to you in the question. So only what they want something, this calculation. They want what? IC, IB and ICU. So you just apply KCL in the outer circuit, you will get answer. KVL in the outer circuit. Or in the input circuit, we can apply KVL here. This is 5 volt. So minus 5, I'll move it like this. So minus 5 and then plus 200k into IB plus PVE here. So all the values we keep, we'll get correct answer for this question. So you could try this question by yourself, and its answers will be I'll be giving. Pehla answer it is how much IC value. That is 2.15 milliamps. Okay, so that is IC. IB, that is equal to how much? 21.5 microampere. This is IB, and IC something. I have written this 2 is value 2.15. So IE value minus IB plus IC. There's some. From this I can get the answer. Okay, so this is done. I think all values you can do in this format. So now the today's class I'll close to here. You can ask your doubts, whatever I taught in the today's class. Based on that, you can ask, or in the previous classes also you can ask. And from the next class onward, I will be taking most of the questions. More questions I will be taking, but before that, theory will be there. So that theory I need to complete, like early effect and all, and alpha increases how, and emitter current increases how. Those things we'll understand in the next class, and we'll come to the basic concepts of BJTs and its applications. So those things we will see in the next class. I will try to finish the most of the part of BJT, and it will be done for you, so that the exam you will be comfortable with the things, whatever you know. So if you have any doubts, you please ask, otherwise I'll close it now. Little early I'm closing, 10 to 15 minutes early, but today it will be up to here only. Okay, so in the next class I may extend a little bit. That's all. Thank you. If you have any doubts, you please ask quickly. Am I audible to all? Voice is fine. I think it is okay for everyone. Whenever any problem comes, please let me know.